going to take a look at finding the solution to a question like this, where it's asking us to write it in the form a plus bi. So there is a way that you could use De Moivre's theorem to find the answer to this, but for this video I'm just looking at how would I do it using exclusively rectangular form without going into polar form. So we're going to take a look at that now. So what I'm going to do first is I'm going to say that the square root of a complex number is equal to a complex number. So I'm going to say that that is equal to a plus bi. I now want to get rid of my square root, and how do I do that? Well, to get rid of a square root you do the opposite, which is square, and if I do it to one side I have to do it to the other. So I'm going to square both sides here. So this and this will drop out, and on the other side I'm going to be left with a squared plus 2abi plus b squared I squared. And what we know about I squared is that it's actually minus 1. So I'm going to actually have here a squared plus 2abi minus b squared. And all of that is equal to 9 minus 40i. Now what I have is an equation on the left that contains a complex number, and on the right that has complex number, meaning real parts and imaginary parts. And what you hopefully will remember is that we can only ever let real numbers equal to real numbers. So 9 has to equal to a squared minus b squared. So I'm going to write that in here. 9 is equal to a squared minus b squared. So I'm letting the real part equal to the real part. I'm now going to do imaginary equal to imaginary. So minus 40i is equal to 2abi. So I'm going to write that in over here. So minus 40i equals 2abi. Now what I have, if I cover up all that, now what I have is simply two equations with two unknowns. And if you are met with two equations and two unknowns, immediately your brain should be going, I'm asked to do a simultaneous equation here. What your brain should also be thinking about is what type of simultaneous equation is it? What's the process that I'm going to run through to solve this? And because this is a quadratic, you should know that you should be getting one of them written out as a equals or b equals, and then subbing it back into the nonlinear, into the quadratic. So I'm going to now get this out, and it's going to give us, if I simplify it, I'm going to divide both sides by I first, and I'm going to have 2ab is equal to minus 40. I'm going to divide both sides by 2, and I get ab is equal to minus 20. And then I'm going to get, let me substitute in for a. So I'm going to say a is equal to minus 20 all over b. It doesn't matter which one you rearrange it to be. I like to choose a because when I sub it in, I don't have to worry about squaring it and then changing the sign. So that makes it a little bit easier if it's going in here where it's positive. So I'm now going to substitute this guy in, which is the orange part. I'm going to sub him in every place that I see a in the nonlinear equation. So I'm going to have this becomes 9 is equal to, and I'll just change colour so it's really obvious where it's coming from, minus 20 all over all over b, and then we're going to have it squared. And then we have minus b squared. I'm going to square this out now, and if I square that out I'm going to have 400, because it becomes a positive, square the top and the bottom according to our indices laws. And if I square the bottom I get b squared, and then it becomes minus b squared here. I'm now going to get rid of that fraction because I don't like the look of it. I'm going to multiply everything through by b squared. If I do that I'm going to have 9b squared is equal to 400 minus b to the power of 4, because when you multiply through with indices of the same base you add the powers. The next thing I'm going to do then is I'm going to rearrange this equation so that it's structurally similar to other quadratics that I've answered. So what I mean by that is I'd like to have it so that all of the values are on one side and that it's equal to 0. To do that then I'm going to add b to the 4 to both sides. So I'm going to have b to the 4 is equal to, I'm going to add it to both sides. So b to the 4, and I'm going to have plus 9 b squared. I'm going to subtract 400 from both sides and I'm going to set it equal to 0. Now, some of you might be confident enough to tackle that and you might see straight away how it factorizes, and other people might start to panic a little bit with the b to the 4. What I would suggest you do if you are panicking when you see this is you break it down into b squared squared, because that still gives us b to the power of 4. Then I'm going to have plus 9b squared still, and then minus 400. What you might notice is that the b squared appears in two places. So it actually appears here and here. So what I'm going to do now, just to make life easier, I'm going to say let x temporarily be equal to b squared. And I can now write this as x squared, so take out the b squared, replace it with x squared plus 9x minus 400 is equal to 0. And then I have that. So I'm now going to try and solve this, and I break it down into the factors that I'm used to, the procedure that I'm used to running, which is I split it into two brackets. I put the x's at the start of each bracket, and then I look at factors of 400. That'll give me 9, so it's factors of minus 400. So what I'm actually going to do is one of these has to be plus and one of these has to be a minus. And if you check all the factors, you'll actually find 25 as one of them, and you're going to find 16 has to be the other one to add to 9. So what you then get is you get x is equal to, and we're going to get here x is equal to minus 25, and in this one we get x is equal to 16. Now remember, that isn't what we had in mind for the equation. We wanted to find b, not x. So I need to go back and think, what was the connection between x and b? So x is equal to b squared, so we introduce it again. So we're going to have b squared is equal to minus 25, or b squared is equal to 16. Now, we're not going to be able to do this one because at the start, when we introduced the a plus bi, I should have really written it down, that a and b are elements of the real number set. So I don't and can't have a solution where I have b equal to, or b squared equal to minus 25, because that would produce, if I ran through it, it would give me the square root of minus 25, and you should know that that produces an imaginary number. And if it produces an imaginary number, then it can't meet the conditions of our a plus bi that we introduced at the start. So that's why we do not take this route. But what I can do is I can do b squared is equal to 16. So if b squared is equal to 16, I can say that b is equal to the square root of 16. Now be extra careful here. If b is equal to the square root of 16, then b could be equal to plus or minus 4. So there's two solutions there. b is equal to plus or minus 4. So that's often overlooked. There's two answers here. Once I have b, then what I can do is go back to my equation that had a in it, which was this guy, and I'm going to say that a is equal to minus 20 over b. I now know that b is equal to plus or minus 4, so let's do the positive 4 for this one. If b is equal to positive 4, then a is equal to minus 20 all over 4, so I get minus 5. And then writing that out in the form a plus bi, I'm going to have minus 5 plus 4, and then remember it was a plus b I. I do the other one then, and I'm going to get a is equal to minus 20 all over b again, but in this one I'm going to do it for b is equal to minus 4. If I do that out, then I'm going to have a is equal to minus 20 all over minus 4. If I do that out, I'm going to get 5 for a, and then again write it in the format a plus bi. Now it's plus bi, but in this case we had b was minus 4, so we filled in minus 4 and then our I. So we got two possible answers for the a plus bi, which you should get because it was the square root. You should get two solutions.